Gases consist of numerous molecules that move and collide randomly, exchanging kinetic energy and momentum. However, we do not perceive this activity. Tracking each molecule individually is unfeasible due to the sheer number of them. Consequently, a new method needs to be created. One method focuses on recognizing measurable properties and establishing the relations between them, whereas the other involves sophisticated mathematical methods derived from the statistical physics. Both methods should produce consistent results. Let's start with a few fundamental assumptions about gases to make our analysis easier. First, we consider the size of gas molecules to be insignificant, and we assume that collisions between these molecules are perfectly elastic, meaning there's no loss of kinetic energy. This type of gas is known as an ideal gas. The key measurable macro quantities in gases are pressure, volume, and temperature. By measuring these properties of an ideal gas under different conditions, researchers have formulated an empirical equation for ideal gases, referred to as the ideal gas law. The term empirical indicates that this formula is not based on previously established equations, but is instead derived from mathematically relating experimental data without a comprehensive grasp of the fundamental physical principles involved. Lowercase letter n represents the number of moles, and R denotes the universal gas constant, which is valued at 8.3145 joule per mole Kelvin. Let's explore some fundamental principles related to gases. The total number of gas molecules in a container is represented by the letter N. When this quantity reaches 6.022 times 10 to the power of 23, it is referred to as Avogadro's number, which signifies 1 mole of a substance. To determine the total moles in a container, the total number of molecules must be divided by Avogadro's number. Statistical methods for analyzing gases, developed by Maxwell and Boltzmann, led to the creation of a statistical distribution of molecular speeds in a gas contained at a certain temperature. Instead of measuring the speed of each molecule individually, the emphasis is on finding out how many molecules have a specific speed at that temperature. Each point on the red line represents the quantity of molecules that have a particular speed v at a specific time and temperature. At a different moment, under the same temperature conditions, other molecules will exhibit that speed due to the frequent collisions that have led to transfer of kinetic energy and momentum among them. Nevertheless, the overall count of molecules moving at the same speed will stay fairly constant. Using further mathematical methods, the average speed of the molecules was calculated for a given temperature. Because kinetic energy is directly linked to speed, the average kinetic energy of the gas molecules was also calculated. According to Maxwell and Boltzmann, this relationship is 3/2 kT, where K represents Boltzmann's constant, which is 1.38 times 10 to the power of minus 23 joule per Kelvin. It is important to recognize that Boltzmann's constant is a very small value, which makes sense because it indicates the change in average kinetic energy of a single molecule when the temperature changes by 1 Kelvin. However, since there is Avogadro's number of molecules in 1 mole of a substance, the change of the total kinetic energy for 1 mole of gas per 1 Kelvin is about 8.3 joules. This figure aligns with the universal gas constant R. Therefore, the link between Boltzmann's constant K and the universal gas constant R can be expressed as K equals R over NA. What we need to do now is to relate these statistical findings to the empirical equation of the ideal gas. Let's examine a cylinder with a piston that holds a single gas molecule at a temperature T. This molecule oscillates along the cylinder's axis, striking the piston with each movement. Each time it collides with the piston, the molecule's momentum shifts by 2p. Prior to the collision, its momentum is p, and following the collision, it becomes minus p. Therefore, the change in momentum, delta p, is calculated as p minus minus p, resulting in 2p. If we consider the average speed of the molecule to be v, the time interval between two collisions with the piston is 2L over v. This time is calculated by dividing the distance a molecule travels by its average speed. The force that the molecule applies to the piston can be described by Newton's second law as delta P over delta T, which can be expressed as 2P over 2L over V. By simplifying this and using the double fraction rule, we arrive at the equation for force F as PV over L. Since mv denotes momentum, this expression can be rewritten as mv squared over L, suggesting a relationship to kinetic energy. As we measure pressure in gases, it makes sense to relate force to pressure. Pressure is defined as F over A, where A represents the area over which the force F is applied. This means that force can be expressed as P times A. By substituting this into the earlier equation for the force exerted by a molecule on the piston in the cylinder, we arrive at the revised equation P times A equals mv squared over L. By multiplying the whole expression by L, we arrive at P times A times L equals mv squared. Given that the product of the cylinder's base area A and its length L equals its volume V, we can rewrite the expression as P times V equals mv squared. P times V equals double the kinetic energy of a molecule. When we replace the average kinetic energy of a gas molecule with the Maxwell-Boltzmann expression, we get P times V equals 2 times 3/2 kT, which simplifies to 3 kT. This statement refers to an individual gas molecule. In a cylinder containing n gas molecules, 1/3 of them travel along the axis of the cylinder, while 2/3 move in directions that are perpendicular to that axis, given that there are 3 spatial axes. As a result, the overall impact on the piston can be expressed as 1/3 of the total number of molecules in the cylinder. P times V equals n-thirds times 3 kT. By cancelling out the 3's, the expression reduces to the ideal gas law, which is expressed in terms of the total number of molecules as P times V equals nkt. To rewrite the previous equation in terms of moles, we need to replace Boltzmann's constant with R over Na, where R is the universal gas constant, and Na is Avogadro's number. This leads to the ideal gas equation in its final form. P times V equals nRT, where N over Na indicates the number of moles in a cylinder, represented by the lowercase n. Thus, the empirical equation of the ideal gas state is validated and explained using the principles of the kinetic molecular theory of gases.